Okay, students, we're going to do part C of this activity. In part A, we made a test solution that was 0.200 molar in viridis. In part B, we used that test solution to derive a spectrum and find what is the wavelength of maximum absorbance. In the example that I gave you, we found that absorbance was maximal at 630 nanometers. Now, in part C, what we're going to do is we're going to obtain a solution of viridis of unknown concentration, and we're going to try to determine what is the concentration of that unknown. To do that, we're going to use a Beer-Lambert plot, and you already saw a little bit of how that works in our introductory video. But eventually, we will build a plot, a graph of the absorbance of the solution at the maximal wavelength, which in this case was 630 nanometers. It's important that we indicate that. And then we're going to plot that against the molarity. In other words, we're going to have to make several solutions of different concentrations of viridis. But here's the thing. If we were to do each one of these from scratch, we would use a lot of glassware, spend a lot of time, and then risk that the solutions we end up actually don't match the one we used already. So let's do this. Let's take this test solution that we already have, and let's build a set of dilutions of it. So what we're going to do then is we are going to dilute this. And so by preparing dilutions of this original test solution, we will have a set of data points here of different molarities based on the one that we use to build that spectrum. And according to what we discussed, the Beer-Lambert plot should give you a straight line, which means that when you plug it into Excel, it'll give you an equation of a line, right? Y equals mx plus b, where y would be the absorbance and x will be your concentration. And so once I have my Beer-Lambert plot and I have the equation of the line, if I put my unknown and determine its absorbance, I can use the equation to solve and find what is the molarity of that unknown. So let's get ready. Okay, students, this is part C of our spectroscopy activity. As you can see, I've relocated here to the bench where the spectrometer is. In part A, we took a stock concentrated solution of this compound viridis, and we made a 0.200 molar solution. This is our test solution. We put it in a beaker after we made the solution so that we could reach in and do the next part. In part B, we did a spectrum of absorbance of this solution, and we estimated that our lambda max, in other words, the wavelength of maximum absorbance, was going to be 630 nanometers. So we have the spectrometer set back to 630. Let me show you some of the equipment we're going to be using, some of the glassware, and then I'm going to walk you to this next part as we make specific dilutions of our test solution of viridis. We're going to have 6 test tubes that I've labeled from 0 to 5. And as you will see later, the number there represents the number of milliliters we're going to add of our test solution to be diluted with distilled water. To make these solutions, we're going to use what is called a volumetric pipette, and I'll describe its use later on. And these require us to utilize an adapter to absorb and dispense the liquid in the pipettes. We might need later on a couple of these dispenser pipettes. We sometimes call them Pasteur pipettes, right? And of course, we want to have our CHEM wipes ready and our cuvettes so that we can analyze the absorbance in the spectrometer. For convenience sake, because cobalt 2 chloride, which is the solution that you're going to be using, it's not the one that I'm using here, but assuming that we have a concern about chemical waste management, what I've done is I've placed a beaker where I'm going to put my waste in here so that at the end of the activity, I can take this to the proper waste container where I'll dispose of it, okay? So let me turn the camera around and let's look at what we're going to do in this section. Okay, I relocated to the other bench because I didn't want the noise from the spectrometer fan to interfere with our audio here, but I have my test tubes that have been labeled from 0 to 5. And remember that what we're trying to do is take our test solution, which is 0.200 molar in viridis, and make dilutions of it in order to get specific molarities that we can use in an analysis of absorbance and to build a Beer-Lambert plot, okay? So this is where it goes. Now, of course, we could start with the solid viridis and calculate how many milligrams and how many milliliters and what have you to make these molarities, but you can imagine the time cost in that and also the abundant use of glassware that we then had to clean or dispose of. So since we already have a spectrum for this specific solution, it is better to start from here and make our dilutions directly from this solution. Now remember, we need to keep a level of precision that gives us the most accuracy. So instead of using a graduate cylinder, we're going to use what is called a graduated pipette. And you can see where graduated pipettes are also labeled on the side. This one goes from 0 to 10 milliliters. It's marked in units of milliliters, but it's also subdivided into intervals of 0.1 milliliter. That means that when you record a measurement with this instrument, you record to one more decimal, right? So to 0.00 milliliters. Now, what we're going to do is we're going to use this particular instrument in order to deliver 0, 1, 2, 3, 4, 5 milliliters respectively into each one of these test tubes. Now, when you receive the graduated pipette from the stockroom, there may be some little droplets of water that were left over from when it was washed, and that's distilled water. However, we don't want our solution to get partially diluted by any residual water in here. So the thing we do is, much like we did with burettes before, is we condition it. So the way this works is you have this adapter. It has a wheel. When you turn that wheel, the piston goes up and creates suction, so it draws in the liquid. And then you can expel it either by pushing this trigger on the side, or the way I like it, because it gives me more control, is to pull this out quickly, hold the mouth of the pipette with your finger, and then very slowly release pressure. That way you can control the flow. So the first we're going to do is we're going to condition the pipette. So I'm going to attach this thing here very carefully, and then this was why I had my solution in a beaker so I can dip into it. And now I'm going to draw up a certain amount of the liquid in there. You can see it going up the pipette there. See it there going up? It's a little slow. There's a little drag between when I pull the little wheel here and the liquid goes up. And now what I'm going to do is very carefully and very rapidly, I'm going to keep the tip of the pipette touching the glass. And then what I'm going to do very quickly, I'm going to remove this and hold it with my finger. so that I have a few milliliters of liquid in there. And then like I did with the burette, I'm going to turn it on its side and kind of roll it around, so that I can get all of the interior of the pipette coated essentially with my solution. And then I'm going to drop it into a waste container. Depending on how much water was in the pipette when you got it, that's kind of like how much of this you have to do. Maybe you had to do it twice. In my case, mine was fairly dry, so I'm just going to do one wash. And so you can just let it drip in there. And we're going to be ready now to assemble our set of solutions. By the way, don't blow on it on the top, okay? Don't blow it on top. Just let it drip. That last drop in there, you touch it to the side of the beaker to let it fall down. And that little droplet at the bottom, if you are interested, it's typically calibrated, but we're not going to use that because our pipette goes from 0 here to 10 here at this line. So we never want to go below that anyway, all right? Okay, so let's get ready to do our dilutions. Remember, the idea is to put 0, 1, 2, 3, 4, 5 milliliters in each. So we'll probably have to do a few rounds of this. Remember, the pipette is calibrated in milliliters, but notice that unlike the graduate cylinder, they're kind of like inverted. It starts with 0 and it goes downwards. Again, like a burette, because you're interested in measuring the volume of liquid you've delivered, not the volume of liquid that's left in there, all right? So once more, what I'm going to do is I'm going to set up my adapter here. I'm going to attach it to the top, make sure that it's tightly sealed, and then I'm going to dip it again into my solution, and I'm going to draw up a bunch of the liquid into the pipette. Again, be careful because, like I said, there's a little drag between turning the wheel up here and the liquid actually going in. And, you know, depending on the width of the pipette and the length, you might be able to fill it up completely, you might not. I'm going to see how far I can take it here because I want to go like a few tenths of a milliliter above 0 if possible. That way, when I turn the pipette over, well, that's as far as it'll go. It went exactly to 0. It's not going to help me a lot because when I pull this out and put my finger on, it's going to lose some liquid. Now, if you want to use this trigger on the side, you can. I find it a little hard to kind of like manipulate, to deliver accurately. So I'm going to very quickly pull this out. I'm going to hold it. And right now, see, it fell under the 0 mark. So what I'm going to do is I'm going to touch the tip to the beaker where it was, and I'm going to let it flow out a little bit until it gets to 1. I can measure it at 1. Okay, so I'm going to bring it down to the 1 mark. All right, and then I'm going to pull it out, and then what I'm going to do is I'm going to take a CHEM wipe, and I'm going to wipe the outside very gently to avoid having liquid on the outside. So now I have my pipette at the 1 milliliter mark. The meniscus is right on the 1 milliliter mark. Actually, I think I missed it a little bit. Hold on. Let me adjust it. Very good. And now in test tube number 1, I'm going to put 1 milliliter. So I'm going to go from 1 to 2, right? So again, I'm going to touch it to the glass, and I am going to slowly let it flow out until the meniscus of the pipette is at the 2 milliliter mark. And I'm going to try to see if I can show it to you when it's done. I'll try to pull in a little closer to the camera so you can see it. Okay, so there we are. We are at the 2 milliliter mark. There's 1 milliliter in here, and I'm going to put 2 in the next one. So if I'm at the 2 milliliter mark, where do I have to go? Right, I have to go to 4. So I'm going to, again, touch the tip of the pipette to the side of the test tube. And now I'm going to let it go. I'm going to release my finger hold. Sorry, you can't see that. Until it goes to the 4 milliliter mark. There we go. And that's 2 milliliters in there. In the next one, I'm going to put 3. So if I started with the 4 mark, that means I have to go to where? Right, to the 7. So I'm going to go to the 7 milliliter mark here. Again, same way. There we go. Excuse me. So that's 3 milliliters. So I'm going to have to refill the burette, and then I'll come back and I'm going to put 4 milliliters in test tube 4 and 5 milliliters in test tube 5. And so I'll come back when we're ready for that. Okay, I am finished. I have my test tubes in which I have 0, 1, 2, 3, 4, 5 milliliters respectively of my test solution. What I'm going to do now is I'm going to add distilled water in order to bring the volume of each one of these samples to a total of 5 milliliters. Don't forget, because of the precision of the graduate pipettes, we are talking about a total 5.00 milliliters. And again, I don't know if I mentioned this before, but because these are dilute solutions, we're not concerned about the volumes not being additive like we were when we make the initial test solution. And so for that reason, we're going to assume that in this case, the volumes are going to be additive. Now for this part, I'm going to use a clean graduated pipette. I put my distilled water in a beaker so I can reach it. So what I'm going to do is I'm going to go kind of in reverse. So since this already has 5 milliliters, I put 0 water here. This one has 4 milliliters, so I put 1 milliliter of water, and then 2 milliliters of water, and so forth. So let me do that again. Once more, you're going to take your pipette, you attach the adapter, you dip it in the water, you suction the water that you're going to need. I'm going to go all the way up to past the 10 mark, if possible. Again, I pull it out, kind of touch it against the side of the beaker. Very rapidly, I'm going to take this out and put my fingers in there. Oops, I got a bubble in there. That's okay. I'm going to touch it. I'm going to bring it down to in this case, it'll go as far as the 2.00 milliliter mark. And then what I'm going to do is with the CHEM wipe again, I'm going to wipe it on the outside and I'm going to come in, and I had to deliver 1 milliliter to this test tube number 4, right? So I'm going to go from the 2 milliliter mark to the 3 milliliter mark, right? The next one requires that I put in 2 milliliters of water, so I'm at 3 now. So where do I go? That's right, I go to the 5, so I'm going to go down to the 5 milliliter mark. Again, notice that I'm always touching it to the side of the test tube so that it'll deliver all the way in. The next one needs now 3 milliliters. I'm at 5, so I'm going to go down to 8, right? And then I'll have to refill. So when I'm done, we'll come back and see the final results. Before we go on, let's take a quick look at my student Wanda's lab notebook here. This is going to be part C. Notice she's already set it up. Here are the test tubes. Of course, there's no test tube 0 because that's going to be our blank essentially. And then she's going to register here the absorbance at 630 nanometers. We decided from part B that that was a good approximation of the maximum absorbance wavelength, or lambda max. And we don't want to wait until we have the actual spectrum to see if there's any discrepancies there. We'll check it later. Normally, you do this lab in the same day, so you want to work a little quickly. And then we're going to have an unknown. Ultimately, that's our goal, is to find what is the concentration of viridis in our unknown solution. All right? So that's our data set. Now let's look at our setup here. I brought our test tube rack over here. You can see that the spectrometer is set at 630 nanometers. It's blinking right now because there's nothing in the chamber. So what we're going to do is, of course, we're going to set up again our study. We're going to use these cuvettes. These might look a little different than the ones that we use for our spectrum. These ones have like a line marking that we're going to use to line up with the line in the chamber entrance, right? The important thing is that the two cuvettes should be of the same batch, the same brand. That way we assure that they have the same optical properties, and that's not going to interfere with our results. So, of course, we're going to have one of them be our blank. So let's go ahead. We're going to use test tube 0, which is our just water. We're going to use that as our blank. So we're going to take a sample there with a clean dispenser pipette, put it in our cuvette. I should go to about 1/3 of the way up, right? I'm going to leave that dispenser pipette in there, and I'm going to take this and I'm going to put it in the chamber so I can recalibrate the spectrometer to 0. Make sure you line up the cuvette with the chamber's marking in there. You bring it down, and now we have to use, remember, we're going to use this knob over here to set it to 0. You don't always know which way to turn it, so just take your time, be careful. It's not way, way off. So that's close enough. We're going to leave it there. Let's let it sit a little bit, and then we'll reset it before we start our measurements. Okay. Now, in our test cuvette, we're going to put in our solutions that we made of viridis. Now, since, as you can tell, they go from more dilute to more concentrated, and actually test tube 5 is the test solution itself, which we have measured. So it'll be interesting to see how close the measurement comes to the one that we did before. It might be the same, it might be a little different. It depends on whether you use the same cuvettes or you did it the same day or whatever, okay? So one of the things that I didn't do was when I added the water, I didn't really mix it. So what I'm going to do is when I take my dispenser pipette, I'm going to go in there and squeeze this a few times just to make sure that it's well mixed, all right? And then I'm going to take that sample of the liquid in test tube 1, and I'm going to start with that one. Again, put it in my cuvette. And then just to make sure, I'm going to take a CHEM wipe, and I'm going to give it a little wipe down because I may have touched this accidentally. I didn't make that mistake with the cuvette in the blank. And now I'm going to replace this into the chamber over there. Again, make sure they're lined up properly. I'm going to put it in there, and let's see what it reads. It's reading 0.396. So I'm going to come back here to our lab notebook that Wanda had set up for us, and we're going to write that number down, 0.396. We typically don't have units for the absorbance because, as we saw in the introduction, it's a logarithmic kind of function. Okay, so I'm going to continue. Now what's going to happen is, because each one of these solutions is more concentrated, I can use the same dispenser pipette as long as I'm going from less to more concentrated. So what I'm going to do is I'm going to take out my cuvette. I'm going to use this to remove the liquid that's in there. I'm going to put it back in its test tube, empty it out, and then I'm going to use the same dispenser pipette to suction some of the liquid into. Now remember, I want to mix it a little bit to make sure that it was properly mixed before, properly formed in the solution. And then I'm going to put it in the cuvette, leave the dispenser pipette in the test tube, line up the cuvette again with the chamber, close the door, and let's see what it says. It says 0.446. So I'm going to come back here, and I write that down, 0.446. And I'm going to continue on, okay, until I have a full set of data from all 5 test tubes, and then we'll be back. All right, here is our complete set of data. And one thing you notice is that as the concentration increases, the absorbance also increases. You should see an upward slope in there, right? If you don't, then something went wrong, or if you see some dips here or there, maybe your solutions were not done properly. The other thing that you notice is that this value here came out a little below what we obtained in the spectrum, right? And notice that these are all primary data observations, so I'm writing them in ink. If I make a mistake, I'll have to cross it out. So this is a little below what the spectrum showed, which I believe was 1.045. So yeah, there's a little variation always. We use different cuvettes. There's different variations. The instrument itself, sometimes varies a little bit, but that's okay. Notice our next goal is to have an unknown. We're going to measure its absorbance, and we're going to record it in here. So at the stockroom, let me turn this around. At the stockroom, Wanda obtained a test tube that had an unknown in it, all right? And we're going to use that to do our test. So we have our blank cuvette here. Let's check it again just in case. Let's make sure that we have it at 0 still. So I'm going to put in the blank cuvette again. This is the one essentially from test tube number 0. And yes, it's okay. It's within the limits there. We can probably re-zero it a tiny bit. I'm sometimes hesitant to do this, right in the middle of an experiment. But the variation is very minimal there in the, thousandths of decimals. So now what we're going to do is, again, we're going to take a clean transfer pipette. We are going to take a sample of our unknown. We are going to put it in our test cuvette, which we should have cleaned before, hopefully. It was dry. Make sure that it was free of any solutions in there. Wipe it down, and now let's see what the unknown says. Take out the blank, put in the unknown, and it's reading 0.570, 0.568. So I'm going to come down here to Wanda's lab notebook and write it down, 0.568. Okay, so what we're going to do next is we're going to take this data and we're going to put it on Excel so we can draw a Beer-Lambert plot, find out what is the slope and the intercept of that graph, and use that equation to find out what is the molarity of our unknown. All right, so now what we have is we have a bunch of glassware that we had to dispose of. Remember that in most cases, your chemical that you're using needs to be disposed of properly. And so what I would suggest is that you pay attention to your instructor's directions. In most cases, what we will do is we will take all this and pour it into your waste beaker and then take that to the appropriate chemical waste container. And the glassware will have to be rinsed out properly, and then before it is returned, make sure that it's all rinsed out, all right? You don't have to pour the washes of the glassware into the waste container, only the primary chemical waste. Okay, I hope you enjoyed that. Let's go ahead and work with the numbers. One thing we'll have to do before we assemble the Beer-Lambert plot is, remember, we're not plotting absorbance against the test tube number. We had to plot the absorbance against the molarity of each one. So let's do a sample of how do we calculate the molarities. Once more, this is a dilution problem, so we use the dilution formula. M1 times V1 equals M2 times V2. Again, the problem we sometimes have is who is who? Well, remember, you started with a test solution that we prepared and which was 0.200 molar. So M1 here is the molarity of the test solution. The test solution. That means that V1 is how many milliliters of test solution did we use? V2 is not the volume of water, it's the final volume of each test tube. So in this case, this is the final total volume. Right? So that means that what is the unknown here? Well, it's the molarity of the diluted solution. All right? That's what we're looking for. So let's do an example for test tube. Let's say test tube number 1. This is just an example. So we're going to rearrange this, right? So M2, which is our unknown, is M1 times V1 divided by V2. Notice that regardless of the units that we use for the volumes, they're going to cancel out. So we can leave it as milliliters. Okay, so our test solution is 0.200 molar. Test tube number 1, remember the number tells you how many milliliters of test solution you put in. So that was 1.00 milliliters. And then your final volume is what did you end up having in the whole test tube? Right, we said 5 milliliters, right? But of course, we have to adjust for sig figs, so that would be 5.00 milliliters. Remember that we added these volumes using graduated pipettes, which have a precision of 2 decimal places. I'm sorry, I apologize for the mistake in the original recording. Let's try to do this calculation here on paper so we can see how it works. Again, we're going to use a dilution formula to find out in this example what would be the final molarity of viridis in test tube number 1. So what we did was we said that M1 is the concentration of the test solution itself. So that would be 0.200 molar. V1 would be the volume of that solution that we added to this particular test tube, and that is 1.00 milliliters. And then we divide that by V2, which is not the volume of water added, but the final volume of the solution, which for every test tube in this case is going to be 5.00 milliliters. So the milliliters will cancel out, and we can do this operation here. Let's say that we do it over here. So I have 0.2 times 1 divided by 5 equals 0.04. 0.04. Now, all of these numbers here have a 3 sig fig precision, so we need to make this go to 3. These zeros, our leading zeros, are not significant, so technically we would have to add 2 zeros here to make this have 3 sig figs. As I'll say in a few moments, you got to realize that because our molarities are only going to 3 decimal places, technically
when you deal with this in your graph, it'll probably only go as far as the third decimal place. And thank you so much.
Now, when you plot the graph, you're going to end up with some of these dilutions being, in the first 3 decimal places. So you'll end up having to drop that last 0. But for now, that is okay. So we would say that the molarity at test tube number 1, or of the solution in test tube number 1, is 0.0400 molar. So we're going to do this exercise now for all 5 of our test tubes. And then we're going to use that data later on when we have the absorbance data to plot a Beer-Lambert